the integral basically of the term in the numerator. So C of x and C of x cancel out. So basically inference through a likelihood F1 or a likelihood F2 gives you the same answers basically for your posterior distribution. And the same thing with the sufficiency principle. Something very important that I'm going to try to emphasize in the follow-up slides as well. Notice that any integrals that appear in Bayesian statistics are integrals in the parameter space theta. They are not in data space. Okay, non-Bayesian statisticians integrate on data space that includes data that they have never observed. Here, all integrals are in the parameter space. This is very important. All right? I mean, this term is the marginalization of this distribution, right? So obviously, I'm going to integrate in the parameter space. This is my posterior, and this is the anormalized version of the posterior on the numerator, so that the integral makes this a normalized posterior distribution. So if you have the posterior, not that you'll be interested just in point estimates, but you may ask, we had a maximum likelihood estimate, so let's formally see all the point estimates that somebody can get with the posterior, okay? So the first one is the map estimate, with the maximum a posteriori estimate is maximizing basically the posterior with respect to theta. This is similar to maximum likelihood, but it differs from maximum likelihood because now there is a log of the prior there. So you know what mathematically does this, why this is a better estimate than the maximum likelihood? This goes back to this concept of regularization, right? If something is not well posed, all right? So maybe maximizing the likelihood is not a well posed problem. Adding this term here stabilizes the optimization problem to give you a nice stable estimate, which is the map estimate, okay? So in mathematics, with no affiliation to statistics, a lot of people will go when they do optimization and add the regularization term. The regularization term in the maximum posterior estimate is the log of the prior. So the prior stabilizes that process, okay? And gives you a good estimate, even if you have very limited data, for example. If you have very limited data, still this will work. Now, the map estimate is, a lot of people would use this, and actually some machine learning books, they prefer to only work with the map estimate, no statistics or anything else, because it's good for what they do. Often it's the wrong measure of the posterior, okay, and we will do examples actually throughout the semester. Another point estimate may be the posterior mean, and this is the calculation of the posterior mean. All right, so you have your posterior, this is the posterior mean. Obviously, you have to integrate in the theta space, and that can be problematic because if this distribution is known through a code, this will require very high dimensional integration, and it will not be an easy thing to get. And of course, you can get a posterior quantile. So for example, you can ask yourself, what's the probability that theta is greater than some value, than 0.5, let's say? And the only thing you have to do is integrate from 0.5, let's say, to infinity, the posterior, okay? So when it comes to point estimates, this is what you need to remember. Map, posterior mean, posterior quantiles. And of course, when we start talking about Monte Carlo methods, we will abandon all of this and work directly in an implicit way through the posterior distribution and figure out how to get samples from there. So let me jump. Slide 49. And I'm going to do one example, trivial. Okay, so coin flipping again, just playing with the posterior. So let's say you want to check basically the hypothesis that the coin is fair, similar to what we had before. Versus the alternative, let's say, hypothesis, H2. So obviously, this is prior probability sum to 1, but we do know what pH of 1 is and pH of 2. So let's say you do an experiment, you flip the coin 5 times, and you measure 5 tails, okay? Would you agree with me that if this is a fair coin, that the likelihood is 1/2 to the 5th, right? I mean, it's a fair coin, probability 1/2 to get heads, so and tails, so the likelihood is 1/2 to the 5th. Now, with the hypothesis that always, let's say, H2 is that always you get tails, what is the likelihood of this? It is 1, all right? So if you want to compare two hypotheses in a Bayesian way, and you form this ratio, by the way, we're going to do this formally, maybe in 1 or 2 lectures using this concept of Bayes factors, but if you want to start with and you want to compare this hypothesis, you will form the ratio of the two posteriors, and then you will decide which way to go based on which one gives you the highest values, okay? So both of these distributions have the same normalizing factor, which is cancelled, so you don't see it here. So what you see is the likelihood with hypothesis H1 times the prior of H1 divided by the likelihood of H2 times the prior of H2. So you plug in this 1/32, and now you see, to make a decision with this data set as which way to go, if the coin is fair or it always gives you tails, unfortunately it depends to a significant degree on what priors you use. All right, so this would not be sort of a very good exercise in inference in a Bayesian setting, because if you already believe that this is a fair or not coin, this will dominate your decision process. Okay? In other ways, this was not a very informative data set, but you may get in life those, and they can throw you out in your decision process. If we do a full Bayesian analysis for a single example, let's say the probability that the coin is will draw heads is from 0 to 1, and we don't really have lots of information, so we take this prior to be uniform, right? So it can be anywhere from 0 to 1, okay? So it can go all the way tails or all the way heads or somewhere in between. So this is our prior. This is the data we collect, and then I claim that the likelihood looks like that. You agree? 2 heads, theta squared, 1 minus theta cube. It's a binomial distribution. And the posterior basically looks like the likelihood times the prior divided by the normalizing factor. And the prior is a uniform distribution. And I would like you to get very familiar with this beta and gamma and all of these distributions, because immediately, if you have theta squared, 1 minus theta cube, this is a beta distribution, beta with parameters 3 and 4. The beta distribution, I remind you, is x to the alpha minus 1, 1 minus x to the beta minus 1. So this will be 2 will be 3 minus 1, and this will be 4 minus 1. So this is, the posterior is a distribution, beta 3 and 4. And depending on the data sets, basically you can get very weird distributions, right? And I have here 3 different data sets, different from this one, and it shows you how the posterior looks like. Okay, it's basically the same example. Now the only difference from the previous example is my prior for theta is not a uniform, but is a beta distribution, okay? And again, you have to recognize that the posterior comes out to be a beta distribution in a closed form. But the way, since I'm going to talk about the exponential family today, notice something interesting. In this problem, if your prior is a beta distribution and the posterior comes as a beta distribution, that's fantastic. And in that case, we call this prior to be what to the likelihood. So when you have a prior that is such that when you multiply with the likelihood, it gives you a distribution of the same family with different parameters, we call the two things what? What's the nice word? Conjugate. Okay, so many things in statistics, okay, they use basically conjugate prior models simply